Hello, we are the UNCC AFRL 4 Senior Design Team, and this is our poster presentation video highlighting our approach to this year's AFRL Design Challenge. The mission given to us by the AFRL was to create a backpackable device that could transport 5 to 10 pounds through 100 yards over rough and rocky terrain in a direct action mission. Some of the criteria given to us by the Air Force is listed here on the left, with a concept of operations image that we have developed ourselves in the bottom left. Our selected design is a hybrid drone/ground vehicle that is a rugged tank-like UGV coupled with a lightweight, heavy-lift UAV as pictured here on the right-hand side with the cargo. It is going to feature a detachable two-component configuration for backpackability so the UAV and UGV can split off. And we're planning on using an autonomous navigation system through the obstacle course, and we're using LiDAR and GPS to make our way through. A brief overview of the mechanical design here is the total drone height is planned to come in at 22.88 inches, the wingspan is 59.4 inches, and the UGV statistics are shown there. We're planning on using 64 square inches of cleated rubber tread that's going to propel the UGV over rough terrain. The Taro T-15 drone frame, as you can see in the bottom left here, was the model that we used for the backpackability of our UAV, and we're planning on using a cargo net system to be able to use Velcro straps in the bottom to be able to set up cargo nets so that anything in the center of our UGV, pictured there, is going to stay in during flight operation. An overview of the electrical design here was in order to prove the electrical viability of the components we selected, we created a power consumption calculator that, given a various obstacle course, we can plug in the technical data from our products and see which one would be the most efficient for our design. Our final selections were the 6-cell lithium polymer battery. We're using a KDE 4012XF400 flight motor, and for UGV we're using the IG42 24-volt DC gear motor. The LiDAR detection system is going to use two 360-degree LiDARs and three single detection LiDAR sensors that are going to point straight forward like a laser pointer. They're going to assist with the flight operations. Pictured here on the right-hand side is a brief overview of the logic we're planning on implementing. Some of the expected results from this was a total weight of 13.55 pounds. This is using manufacturer data, so combining this with the 10 pounds of cargo, we're coming in at a total weight of about 23.55 pounds. Using eCalc, we were able to use a calculation software to help us determine some of the numbers for our drone operation. And so using this website, we had determined a safety factor for mass lift of 2.003. Some driving performance specifications gave us a max ground speed of 2.66 feet per second. And some conclusions from our obstacle course calculation determined that it takes us about 2.06 minutes for one trip, and we can do about 2.09 round trips. Some highlights from our failure mode and effects analysis document were highlighting the problems of flight motor overheat and difficulty flying in low air density. We have a much larger document where we cover much more problems that we had determined. We highlighted some future improvements here and some of our goals for Senior Design 2, including building the prototype, completing testing, and our final design assembly.